today we shall see the equivalence between regular grammars and finite state automata. We have seen the definition of a deterministic FSA, a non-deterministic FSA and a non-deterministic FSA with epsilon moves. All are equivalent as far as acceptance power is concerned. Given a non-deterministic automata with epsilon moves, you can remove the epsilon transitions and get an equivalent non-deterministic FSA, and given a non-deterministic FSA, by subset construction we can find the deterministic FSA. Now, in the grammar, what is a regular grammar? A regular grammar has rules of the form A goes to AB or A goes to A. On the left hand side you have a non-terminal, on the right hand side you have a single terminal or a single terminal followed by a non-terminal. First I shall consider regular sets without epsilon. That is, consider languages of the form L where epsilon does not belong to L. Because for epsilon we have to do some slight modification, that I will consider later. But we have to remember that any grammar type 2, type 1 or anything, type 1, type 3, whatever it is, to include epsilon in a language you can do this. To include epsilon in a language, that is, you have the rule S goes to epsilon, which can be applied in the first step only, start symbol going into epsilon, and make sure S does not appear on the RHS right hand side of any production. See, in some cases even if it appears, it may not make much of a difference, and in some examples it may make a difference. We want to be sure, we want to be careful, that is why we make this restriction. Okay. So, first I will consider regular sets without epsilon. I will start with examples and illustrate the construction with examples. Given a regular grammar G is equal to NTPS, construct a non-deterministic FSA without epsilon moves, M is equal to K sigma delta Q naught F such that T of M is equal to L of G. You given a grammar, how will you construct an equivalent automaton? The automaton which you are going to construct is a non-deterministic one. So, the construction is like this. G is equal to NTPS S is the start symbol, N is the set of non-terminals and so on. M is defined as K sigma delta Q naught F. Now, here K is the same, the set of states will be the set of non-terminals plus one final state. Each non-terminal will correspond to a state in K. Apart from that, you have a one more final state, right? And terminal symbols are the input symbols for the automaton, and S corresponds to the initial state, and initial state Q naught corresponds to the initial symbol. F consists of just QF, and delta you have to define. How do you define delta? If A goes to AB is a rule in P, if A goes to AB is a rule in P, you have delta of AA contains B. In automaton you have delta of AA contains B. And if it is a terminal rule, if A goes to A is in P, it is a terminal rule, then delta of AA contains QF. This is the construction. We will see one or two examples, then it will be very clear why we have constructed this way, right. Then the formal proof is by induction on the length of the string accepted and the string on the length of induction on the length of the string accepted by the automaton, and also one way it is like this, the other way it will be induction on the length of the string generated by the grammar, right. So, that formal proof is as usual, so I will omit the formal proof, but informally we will see the equivalence by seeing the examples. Look at this example, S goes to AS, S goes to AA, A goes to BA, A goes to B. What is the language generated by this grammar? This is a regular grammar with a start symbol S and another non-terminal A. And what is the language generated? You can have any number of A's, at least one A, then followed by any number of B's, at least one B, right. So, the language is A power n, B power m, n comma m greater than or equal to, right. Now, use this construction and construct the NFSA. If you use the construction, it will be like this. For each non-terminal you have a state. S is a non-terminal, you have a state. A is a non-terminal, you have a state. Each non-terminal you have a state, and you have a final state QF. Okay. Now, how do you write? If S goes to AA is a rule, delta of SA contains A, is not it, by the construction how we have, if A goes to AB is a rule in P, delta of AA contains B. It is not equal to B because non-deterministic, we write it as delta of AA contains B. Okay. So, S goes to AS is a rule. So, delta of SA will contain S, that is from S to S there is an arc with label A. S goes to AA. So, by our construction delta of SA will contain A. So, there will be an arc with label A going from S to A, and you have A goes to BB, that is delta of AB will contain A. So, there is an arc with label B going from A to A. Then you have a rule A goes to B, it is a terminal rule. If it is a terminal rule, what is the mapping? Delta of AB contains a final state QF. This is non-deterministic in nature because 2 arcs with label A leaving S, is not it? From S, if you read A, you can go to S or A, possible non-deterministic FSA, and you can very easily see that it also accepts the same language A power n, B power m. So, the construction is very clear. If you have a rule, you draw from, if you have a rule of the form A goes to AB, draw an arc with label A from A to B. A will be represented as a state, B, capital B will be represented as a state. Then there will be an arc with label small a from A to B, that is all. And if it is like this, there will be an arc with label small a from A to a final state, that is only one final state QF, that is all. Okay. Let us consider one more example. You have 3 non-terminals S, A and B. S is the start symbol. The rules are of the form S goes to AA, S goes to BA and so on. What is the language accepted? The alphabet is AB. What is the language accepted? Or what is language generated? What is the language generated? String of A's and B's, but the length is a multiple of 3. The length of the string is a multiple of 3, right? Okay. Tried an example, construct a deterministic FSA over A and B, right, satisfying 2 conditions. The string should begin with a A and end with a B, and A is not a subword, is not it? We consider an example like that, and add one more condition, the length of the string is divisible by 3. Now you construct the deterministic FSA. Try it as a homework. 3 conditions are there now. The strings begins with a A and ends with a B. A is not a subword. The length of the string is divisible by 3. Now let us construct the automaton by our construction. There are 3 non-terminals. So corresponding to each non-terminal we have a state. So S is a state, A is a state, B is a state, and there is a final state QF. S will be the initial state. Okay. Now the mappings you have to write. S goes to A means there should be an arc with label A here. S goes to BA means there should be an arc with label B. A goes to AB, there is an arc with label A like this. There is an arc with label B. From B, if you get a can go to S. So, A, B. The last 2 rules, from B After getting a you can terminate. So, there will be an arc with label A, there will be an arc with label B. Note that this is a non-deterministic FSA, but it will accept the same set of strings like the language generated by this grammar. In A or B you can read by going from S to A, another A or B you can read, another A or B you can read. So, going from S to S you will read a string of length 3, then again another 1, 2, 3 you have to end up here. So, a string of length 3 will be accepted. We have assumed that epsilon is not there in the language, that is why this. If epsilon is in the language, initial state will be a final state. So, grammar also you can see that it does not generate epsilon. So, this construction itself should be make it very clear that the language generated by the grammar and the language accepted by the NFSA are the same, is not it? But a formal proof, if you are writing it as a theorem, you must give a formal proof. The formal proof will be, you have to show that LG is contained in T of M and T of M is contained in LG. Okay. And for this portion you will use induction on the length of the string generated in the grammar. For this you will use induction on the length of the string accepted by the machine. It is a general induction proof. So, I will omit that, I will not go into the formal proof. Just for take this example, let us consider A, B, B. How is this generated? Okay. This is generated like S goes to AS, AS, AAS, AA, AA, AAA, BA, AAA, B, B. The generation is like this. Now, if you look at the string and the acceptance, you are in Q naught, the initial state, that is S, S, then SA can give you SRA, again S, reading A you can get SRA, from S after reading A again you can get SRA, from A, S you cannot read a B, from A if you read a B you will go to ARQF, from A again if you read a B you can go to ARQF. Now, the sequence of states which leads you to acceptance is this. This is the sequence which leads you to acceptance. Look at the non-terminals S, 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 A, of course the state is QF. You can see S, 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 A, and it is QF, it is not there, that is all final. So, see the correspondence, the way it is generated it is accepted in the sequence. Okay. That is the idea, that portion formally you have to prove by induction. Okay. So, we will leave that, but examples make it very clear. Now, the other way around, we have to prove the other way around. What is the other way around? Given, now we take a DFSA. given a deterministic FSA, M is equal to K sigma delta Q naught F construct a regular grammar G is equal to NT PS such that L of G is equal to T of M. Now, we start with the deterministic automaton and construct a grammar. Again we assume that epsilon is not accepted. Okay. I will come to the case, it is just you have to make some slight adjustment, that is all. We will take more example with epsilon later. So, you are given M is equal to K sigma delta Q naught F, you are constructing the grammar G is equal to NTPS. Okay. How do you do it? N is the same as K. For each state you have a non-terminal, for each state you have a non-terminal, and set of terminal symbols are the same as the set of input symbols, is not it? Now, what is Q naught? You have to write P and S. S corresponds to the initial state Q naught, and P we have to write. How do you write P? If delta of QA is equal to P, I am writing QA is equal to P, not contains. Why? Because we are starting with the deterministic machine. Q goes to AP is a rule, Q goes to AP will be a rule. Also, so we are able to write the non-terminal rules. There will be some terminal rules, is not it? How do you write them? Apart from that, if delta of QA is equal to P and P belongs to F, if P is also a final state, then you write the rule as Q goes to A. Okay. So, let us, this is all you have written N, T, S, P you have written, and in this case LG will be equal to T of M. So, here LG will be equal to T of M, right. How do you, let us consider examples again. The proof will be, formal proof will be by induction. Take this one. We had it. For the same language L, this is the deterministic machine, is not it? What is L? Language is A power n, B power m, n, m. Okay. Now, we will write the grammar for this. Q naught, the set of non-terminals will be Q naught, Q1, Q2, D. This will be the set of non-terminals. Terminal symbols will be A, comma, right. Now, we have to write the rules. Of course, Q naught is the start symbol, this is the start symbol, right. How do you write the rules? Now, Q naught A goes to Q1. So, you have a rule Q naught goes to A Q1, Q naught goes to B D, right. Q1 A Q1, is not it, or delta of Q1 A is Q1. So, Q1 goes to A Q1, Q1 goes to B Q2, right. Q2 goes to A D, Q2 goes to B Q2, right. D goes to A D, D goes to B D. These are the non-terminal rules. Now, terminal rules, wherever you have Q2 here, Q2 is the final state here, wherever you have Q2 here and here, corresponding to these two rules, you will have terminal rules, that will be Q1 goes to B, Q2 goes to B. But you will realize that we have considered removal of useless symbol. Which is the useless symbol here? D is the useless symbol. So, any rule involving D, D is useless. So, anything involving D you can remove. So, you will end up with this 6 rules. Okay. So, you can generate one A and any number of A's you can generate with this rule, one B you will generate and any number of B's you can generate. You can terminate with this or this. If you terminate with this, there will be only one B. Then after generating many B's, if you want to generate, you want to terminate, you will use this, right. So, the language accepted is the language generated by the grammar is the same as the language accepted by the machine. One more example we will consider. This is a deterministic machine. What is the language accepted? The language accepted should have at least one A. Any number of B's you can have and one A you should have, afterwards you can have anything. So, the language accepted should have a minimum one A. Okay. So, T of M is W, W belongs to A comma B star, W has at least one A. Now, let us write the grammar for this. G is equal to NT PS where the set of non-terminals is the states Q0, Q1, T of course is A, B, Q0 will be the start symbol, and the rules are like this: Q0 goes to B Q0, Q0 goes to A Q1, Q1 goes to A Q1, Q1 goes to A Q1, Q1 goes to B Q1, Q1 goes to B Q1, Q1 is the final state. So, corresponding to these three rules, you must also have a terminal rule. So, you will have Q0 goes to A, here you will have Q1 goes to A, you will also have Q1 goes to B. You can very easily check this. Here the language generated and the language accepted are the same. There are no useless symbols. Roughly you can see that the dead state will correspond to a dead state, or a state from which you cannot go to a final state will become a useless symbol in the grammar, useless non-terminal. Again the formal proof, you have to show that LG is contained in T of M and T of M is contained in L of G, which is done by using induction on the length of the strings generated and accepted. Now, the problem with epsilon. So, the next thing, what happens if you have epsilon belonging to you? When the empty string is also accepted by the machine or generated by the language, how you have to change? Now, first step will be, given a regular grammar, construct an NFSA such that Tm is equal to Lg. This is the way we constructed, is not it? Now, in this case the grammar we take has this property. If you want to include epsilon, only S goes to epsilon is a rule, and S does not appear on the right hand side of any production. So, the diagram which you construct will be something like this, right. In this case, if you want to accept from here, you will go to some other state, but you will not come back to S, is not it? You will not come back to S. The reason is S does not occur on the right hand side of any production. So, any string in L minus epsilon if you take, that will be accepted the usual way you construct, and it will be accepted, right. For epsilon, make this a final state, make the initial state a final state, so epsilon will be accepted. This does not affect the other portion, because you do not come back to epsilon, I am sorry, you do not come back to S, right. Now, the other way around, given a BFSA M is equal to K sigma delta Q naught F, construct G is equal to NTPS. here the q naught is S, you have to just add the rule q naught goes to epsilon. If you add the rule q naught goes to epsilon, the other construction will not be affected, only just you have to add this. But you can also make sure that in this case q naught may occur on the right hand side of a production. You can also make sure that that does not happen. Okay. So, just I will put, see, if the DFSA accepts epsilon, initial state will be a final state, and in that case just add q naught goes to epsilon. Nothing else will be affected, but it will not satisfy this property, is not it? If you want that property also to be satisfied, you have to do something else. Again I will illustrate with an example. Consider this automaton AB strings of the form AB will be accepted, epsilon will also be accepted, other strings will be rejected by going to the dead state. If you want to write, I will not write the non terminals and all, just the rules alone. If you write q naught goes to AQ1, q naught goes to BD, q1 goes to, I will write the D rules in this side, so later on we can remove BD, q1 goes to BQ naught, q1 goes to AD, D goes to AD, D goes to BD, then q naught is the final state. So, you will also have q1 goes to B, this you will have. Now, your initial state is the final state. So, what do you have? Q naught goes to epsilon. Can add. Okay. Now, once you go to D, you cannot derive a terminal string. Right, from D you cannot derive a terminal string. So, all these, D is a useless non terminal, all these rules can be removed. So, I will rub this off. Now, the start symbol q naught goes to epsilon, but it is occurring on the right hand side. Okay. In order to avoid that, what do? You can add a new start symbol S and have S goes to epsilon. And this you will remove. Then whatever is there with q naught, you also have with S, that is, this is a rule with q naught on the left hand side, you also have S goes to AQ1. This S will be the new start symbol, epsilon is derived. Any other string AB will be derived by S goes to AQ1, Q1 goes to B. AB will be derived using this, right. You have to just make a slight adjustment, that is all. So, given a regular grammar, you can construct an equivalent automaton, and given an equivalent, given a FSA, you can construct a grammar. Now, the way we went about this, given a grammar, we constructed a NFSA, but we know that given an NFSA, you can construct an equivalent DFSA by subset construction, and in the other way around, given a DFSA, we constructed the grammar, right. So, a regular set, there are two ways if you consider a regular set. One way is a regular grammar, you can use a regular grammar to generate it. Another is you can use a FSA to accept it. This is a generative device, this is an acceptance device. FSA you can have with epsilon moves, without epsilon NF, you can have a deterministic FSA, you can have a non-deterministic FSA without epsilon moves, a non-deterministic FSA with epsilon moves. All three are possible, they are all equivalent. There is one more way of representing a regular set, that is by means of what is known as a regular expression. Informally, we have used expressions of the form 0 plus 1 star, A star, like that. They are all really regular expressions. How do we formally define a regular expression? Before that, let us just recall some operations on sigma star. This we have studied earlier in the previous course. L1 is a language, L2 is also a language over sigma star. Sigma is the alphabet, sigma star denotes the set of all strings over sigma including the empty string, right, and L1 and L2 are languages, languages means set of strings. Then the following operations you can define L1 union L2, because they are sets operations can be defined. L1 union L2 will be x belongs to L1 or x belongs to L2, the usual set theoretic operation. You can also define L1 intersection L2, L1 bar is sigma star minus L1. The set theoretic operations you can define on this. Apart from that, if you remember, we also defined something else earlier. L1 L2, the concatenation of L1 and L2, what is this? This is a set of strings of the form xy, x concatenated with y, x belongs to L1 and y belongs to L2. What is the concatenation? If x is equal to A1, A2, An and y is equal to B1, B2, Bm, these are two strings, then the concatenation of x and y is denoted as xy, and that is A1, A2, An, B1, B2, Bm. This is a concatenation of two strings. For languages it is defined like this. What can you say about the operator concatenation? Is it commutative? Is it commutative? No, it cannot be commutative. Xy cannot be equal to Yx. Is it associative? Concatenation is associative, right. So, you can without any difficulty you can L1, L2, L3 will be the same as L1, L2, L3. Concatenation is not commutative, but it is associative. So, what do you mean by L into L? Usually denoted as L squared. And you can without any problem you can talk about this. Either you group this way or you group this way, it does not matter because of associativity. So, this is L cubed. In general, L power k is L power k minus 1 concatenated with L, right. What is L0? This also we studied, if you remember in the last semester, it just contains the empty string. Right. So, L star, how do you define L star? This is union of I is equal to 0 to infinity L. The Kleene closure star operation or Kleene closure are sometimes just denoted as closure. L star is union of I is equal to 0 to infinity L power I. What is L plus? Union of I is equal to 1 to infinity. Okay, these things we have studied earlier. For regular expression, we use this. Consider the alphabet. Let sigma be an alphabet. Sigma is an alphabet. Phi, the set of regular expression over sigma star is defined. The set of regular expressions on over the alphabet sigma over the alphabet sigma, or you can say over sigma star, is defined as follows. Phi is a regular expression denoting the empty set we have defined, or we have considered inductive definition of sets. So, here it is we are making use of inductive definitions. These are basis class. Phi is a regular expression denoting the empty set. Epsilon is a regular expression denoting the set having the empty string alone. Epsilon is a regular expression and it denotes the empty string alone. A is a regular expression denoting the set A having the single string A for each A in sigma. For each A in sigma. This is the basis portion. The inductive class is if R1 and R2 are regular expressions representing L1 language L1 regular sets L1 and L2 respectively. R1 plus R2 is a regular expression representing L1 union L2. Okay. R1 plus usually is R, union is defined like that, L1 union L2 is x belongs to L1 or x belongs to L2. R1 R2 concatenated with this is a regular expression representing the concatenation of L1 and L2. R1 star is a regular expression representing L1 star. We make use of these three operators: union, concatenation, and star. Usually this dot you do not write explicitly, it is implicitly understood. Then the extra will come, all regular expressions are obtained in this manner and so on, and nothing else will be obtained. So, this is another example of an inductive definition of a set. For example, you consider A plus B star. What does this mean? Set of all strings over A and B including epsilon. Okay. This is of the form L star. L itself has two strings A and B, right. L has, suppose L has A comma B, L0 is epsilon, right. L is this, L squared will contain all strings of length 2, L cubed will contain all strings of length 3 and so on. So, union over I is equal to 0 to infinity contains all strings of over A and B. Now, this L itself we can look at it as L1 union L2, is not it? This is just A, this is just B. That is why this is represented as A plus B. So, from the base things, by having one operation like this, you are able to get the set. Some more examples. We have considered this A power n, B power m, n several times. We have considered this example. What will be the regular expression for this? What will be the regular expression? There should be at least one A, any number of A's you can have, one B, any number of B's you can have. So, it will be A star, B star. The regular expression corresponding to this is the set of strings over A and B, where A should occur as a substring, where A set of strings over AB containing A as a substring. What will be the regular expression? You can have any string preceding the 3A's, 3A's should occur somewhere in the middle. So, in the middle you must have 3A's, it can be followed by anything. The regular expression for that will be like this. Change this a little bit. Set of strings over AB containing 3A's or 2B's. It should contain 3A's or 2B's in the middle. What will be the expression? It will be anything you have in the beginning, but in the middle you will have 3 A's or 2 B's, right. Then it can be followed by anything. How will you represent the Fortran identifiers? Fortran identity. Fortran, it is not now used, but anyway for example sake, Fortran identity. The length will be 6, it will begin with a letter and afterwards you can have a letter or a digit. So, the expression for will be A plus B up to Z, first has to be a letter, then followed by a letter or a digit or nothing else. You can just have A, B alone also, is not it. So, this will be A plus to Z plus 0 plus to 9 plus epsilon, and you can go up to 6, length 6. So, this power so we have now defined what is a regular expression. A regular expression represents a regular set, right, that we have to prove. So, given a regular expression, we shall see how to construct a non-deterministic FSA with epsilon moves next class. So, from a regular expression we can go to a non-deterministic FSA with epsilon moves. Then we know how to remove the epsilon transitions and get an NFSA. From NFSA how to go to DFSA by subset construction. Then the other way around, given a deterministic finite state automaton, how to find the equivalent regular expression for this. Meanwhile, I want you to think on 2 points. There are 3 set theoretic operations we consider: union, intersection and complement. So, try to prove that if L1 and L2 are regular sets, L1 union L2 is a regular set, L1 intersection L2 is a regular set, L1 bar is a complement of L1 is a regular set. How will you prove this? Think over this, we will consider it later.